Albert Einstein once said, space and time are not about important characteristics of existence, but are some important models of thinking. Hello everyone, I am Anurag and I am going to present the paper titled Space-Time Continuum Metric at the International Conference on Intelligent Computing, Communication and Information Security. Firstly, I would be thanking SKIT Jaipur for hosting the conference and AICT for sponsoring the same. So let us quickly jump into the paper presentation. Here it is me. I am an undergraduate at the Department of Computer Science and Engineering at Government College of Engineering and Textile Technology, Shirampur. This is my guide for this paper, Mr. Piyush Kanti Kumar. He is an assistant professor at the Department of Information Technology, Government College of Engineering and Textile Technology, Shirampur. So, in this paper, we would be proposing a new metric that would help us to compare algorithms. Now, before jumping into the paper presentation, we would like to build up on something which we could use for like working upon later on in this presentation. So, we would start our discussion using a little bit um, introduction on algorithms. So, let us start with that only. Algorithms are a step by step approach to a solution with some mathematical rigor inserted inside that. Now, in this latest world of technology, every problem comes with multiple solutions. Now, there must be some kind of heuristic to uh, determine on which solution should be taken into action. Like the best solution possible at that time according to the required person should be taken into account, right? So the best term is relative in nature. It's quite obvious that this best term is relative in nature. So we will have to select that particular algorithm which should be best according to the person who is getting the need of that particular algorithm to be used. Like the best algorithm for person A may or may not be the best algorithm for person B, but it should be like that this metric that we are proposing should cater all of them literally. So traditionally we have been comparing algorithms based on their metrics of time and space, which seem to work well for like many algorithms. Sometimes we have also seen that space and time are considered trade-offs. If we are low on time, like we want our work to be done quite fast, so we could compromise the space as well in some cases. One of the best example of this could be the Siva Virathathanas. We will be discussing about that later on. But yeah, this was a like little bit of introduction on the algorithms. Now, from the next slide onwards, we will be talking about the pre-existing metrics which we are using commonly. This slide talks about the time complexity. So, time complexity is the complexity of calculation and represents the amount of computer time it takes to execute an algorithm. It is usually estimated by counting the number of basic operations performed by the algorithm, assuming that each basic operation takes a certain amount of time to perform. Therefore, it is assumed that the time required and the number of basic operations performed by the algorithm is related by some constant term. And that is why they are represented by some asymptotic notations. The most commonly used asymptotic notation, though, is the big O notation, or we could say it as the uppercase O notation. This is basically the worst case time complexity. Like we have three types of complexities. One of them is the best case time complexity, in which the algorithm is about to take minimal time. The other one is the average case time complexity, in which the algorithm is about to take like uh, average, like okayish time, and the third one being the worst case time complexity, in which they will be taking the major time that it could take actually. So yeah, this is all about the time complexities. Next, we will be talking about space complexity. So, space complexity of an algorithm is basically the memory that this algorithm is bound to take during its execution process. It is quite simple. It is also execute. It is also represented in the same manner as we used to do for time complexity. The most commonly used asymptotic notation hereby is also the big O notation. This slide we will be talking about the space-time trade-off. I have talked about the space-time trade-off a little bit in the introduction, but yeah, let's see. In practice, both time and space complexity metrics are given equal importance in the aspect of their like importance. They are taken quite safe. But while dealing with real life problems, there might be some cases in which time complexities is given a higher edge over the space complexity. So in that type of scenario, we used to compromise those space complexity a little bit and try to gain more on the time complexity side. So one of the best example is sieve of irritathanis, in which we give a single integer value as input or a single number as input, and we'll try to like guess whether that particular number is prime or not. So basically what it does, it takes a particular range previously and calculates or computes all of those prime numbers that could be inside that particular range and stores that inside its memory. And whenever we are giving a query about a number, that whether it is prime or not, then it checks in that particular list that whether the number that we are trying to search is present in that particular list. If it is at all present, then it will be returning an yes, and in the other case it will be returning a no. So yeah, it is quite like a constant time it will be taking really. From this slide, we will be talking about our metric that we have proposed in this paper. So it is the space-time continuum metric. This metric will be keeping in account of both the complexities, not the like the space and time complexities, which at a sheer aspect is a way ahead of all the pre-existing complexities, which tend to keep in like aspect of unidimensional complexities. Like the time complexity is only going to take about time, and the space complexity is only going to talk about space. So this space-time continuum metric is a metric that will combine both of these dimensions. So yeah, it is going to be like better in sense of dimension. So let us consider an algorithm A of n with space complexity as S of n and time complexity as tau of n. Now, both of them could be represented in terms of their asymptotic notation. Now, we have seen that asymptotic notations of time and space complexity both are taken as same. So, we could conclude them as being gamma. Yeah, this is the appropriate asymptotic notation. We are not getting deeper into that, but okay. Now, Sn could be written as gamma of psi n, and Tn could be written as gamma of phi n. Now, gamma of phi n could be rewritten as delta times phi n plus mu, while gamma of psi n could be rewritten as alpha times psi n plus beta. So, this is like simply regenerating the actual meaning of the asymptotic notation. And one thing to note hereby is that the quadruple alpha, beta, delta, and mu will be constant. Now there should be some value of phi n. Okay, this is the lowercase phi. Okay, so there should be some value of phi n such that phi n should be equal to maximum of these two values, that these two functions, and it would be taken upon as a ratio of this maximum of these two functions and the minimum of these two functions. Now hereby maximum of these two functions could be taken as the summation of these two functions along with the modulus of this is the actually the absolute value. So absolute value of the difference between these two functions. So this is the maximum, while um, uh, taking a difference between them would give us the minimum between them. Now, since this function maximum of psi n and phi n and minimum of psi n and phi n are complementary to each other. Now, since they are complementary, the pair psi n and phi n, that would be giving us the value of maximum of these two functions will be complementary to that particular pair psi n and phi n, that would give us the minimum value of these two functions. Now, due to which two cases may arise. One of them is the maximum of these two functions would be equal to phi n, while the other case is maximum of these two functions would be equal to psi n. Now, firstly, we will be talking about the maximum being equal to psi n, and later on in the presentation, we will be talking about maximum of these two being equal to psi n. So phi n, sorry. So, let's talk about the case one first. So we could fetch the value of psi n from the equation 1 as we discussed here, this equation 1, and we could get the value of phi n from equation 2 as we discussed. Now, in terms of the tuples that we will be getting, we could write psi n as Sn minus beta upon alpha and phi n as Tn minus mu upon delta. Now, as we mentioned earlier, there would be some value phi n that would be the ratio of both of them. We could take this ratio as psi n upon phi n, and using that we could say that Sn, that is the space complexity, would be equal to alpha times the ratio of both of them, that is the phi n basically, multiplied with tau n, that is the time complexity, minus of mu upon delta, added with the constant beta. So it is for this case 1, and even it is the same for case 2 as well. So on a generic note, we could say that the value of Sn, or the relation between Sn and tau n, would be like Sn would be equal to alpha times the ratio of psi n and phi n multiplied with tau n minus mu upon delta. Now, one thing to note about here in this case is we are taking the nearest integer by making use of the floor function over here. We will be taking the nearest integer that we are getting for this ratio. Now, since n is constant during execution of the algorithm, so we could take a 2D plot of this Sn and tau n on polar coordinate systems. We will be seeing that when we will be making use of this space-time continuum metric for breaking the tug between two algorithms. So we will be seeing this. From the next slide onwards, we will be seeing that. So from this slide, we'll be talking about space-time continuum in action. So firstly, we will be breaking the tug of war between selection sort and bubble sort. So for selection sort, we could say that the what do we say, the relation between Sn and tau n would be Sn equals 2 times tau n upon n square plus 1 upon n square. Now we could transform that according to the transformation, tau n Sn would be equal to lambda cos theta and lambda sin theta, and this value of lambda will be a square root of the second power of each of these complexities added together. Now, using this transformation, we could say that the relation for selection sort would be sine theta minus 2 cos of theta upon n square would be 1 upon n square times lambda, and for bubble sort it would be 2 cos theta upon n square minus sine theta would be equal to 1 upon n square times lambda. Now, these two relations could be plotted in the polar coordinate system, and could be demonstrated further. Yeah, so we have done this plotting of these two relations accordingly. And one thing to note hereby is the legends being blue for bubble shot and red for selection sort. So this red one is for selection sort and this blue one is for bubble sort. So one thing that we should have seen in this graph is the slope being constant for both of these two lines in this case. So in this case, both of these lines are having a constant slope, like not constant slope, that slope of both of them are equal, and that is equal to like this gigantic value. So it is something which is not worth explaining in this presentation, though we could say that if we are trying to get edge on the time complexity side, So it is better to make use of selection sort than bubble sort. But if we are trying to get an edge over the other in the case of space complexity, then we could better make use of the bubble sort. So yeah, this representation makes it easier for the algorithmist to like understand which of the algorithm to be used according to their need. So it is quite the useful for them. So the next slide is about the tug between merge sort and heap sort. Both of them are linear arithmetic time kind of complexities. So we could take it as like Sn would be equal to log base n of 2 times the tau of n, and by making use of the transformation we would be getting like sine theta minus this particular value of log times cos theta would be equal to 0, while for heap sort it would be like sine theta minus n inverse into cos theta would be 0. We could again plot this into the graphical representations, and we could get the graphical representations actually. And yeah, so using these graphical representations, one thing is quite clear, that if we are having the value of n being less than 1, then it is quite better to make use of like merge sort if one needs the time space complexity to be improved. But if one needs the space complexity to be improved in the cases of n greater than equals to 1, then it's better to make use of heap sort. But if one is trying to optimize time, then he could make use of merge sort for the values of n greater than 1. Now it is quite obvious that it is like the value of n that we are about to get would be 1 at minimum, like it would be greater than equals to 1 in all of the cases. So we could say that merge sort is a better time saver than that of heap sort. So yeah. Now by this we have reached to an end of this presentation. Now we will be concluding our work. Space-time continuum, unlike other comparators, is a metric to mark the algorithms, but the merit of this metric is that, unlike other metrics, it is not unidimensional. Like other metrics, as I have mentioned previously also, that other metrics are unidimensional, like they will be taking care of space complexity at once or time complexity at once. But this space time continuum metric will be keeping in account of both the metrics, like they will be keeping in account of the space complexity as well as the time complexity. And it is definitely going to help the algorithmists to get a better idea of which algorithms to use in which cases, like according to their needs. Now, there could be scopes of further improvement or further research by extending our works. Like many of us have heard about some third kind of complexity known as bit complexity, which is related to the bits. Like, yeah. So, this bit complexity could also be incorporated in this time and space tug like this. And yeah, it would be a three-dimensional plot in the polar coordinates, but hopefully it would make something great. They are not like it could be taken as account. These are some of the references which we took help from for preparing our manuscript. So yeah, thank you. Have a nice day.